I just came back from a talk I gave at the Haskellers Montreal meetup, and so since it wasn't recorded, I wanted to do it again at my computer so that you can have an idea of what I said. So, let's do it. Welcome to the Haskellers Montreal meetup. We meet here every 2 months to discuss some Haskell topics. Some of them are advanced, such as comonads, and some of them are for a more general audience, such as today's presentation. And since it's for a general audience who is perhaps not familiar with Haskell, I will not give any Haskell code today, because I don't want to spend some time talking about the syntax. Instead, I want to focus on the ideas. So let's begin. Haskell is my favorite programming language, but even though I'm fanatical and I would use it for every possible situation, maybe you're not. And so, since I believe that it's important to always pick the right tool for the job, I wanted to give you both Haskell's advantages and disadvantages so that you can decide on your own whether Haskell would be a right fit for your next project. So one Haskell advantage is that code is very short, and the reason for that is that the language has a few ways to allow you to omit code. Haskell code is also easier to refactor, and there are many reasons to that. One of them is that since Haskell is statically typed, once you begin your refactoring, well, now your program no longer compiles. You have lots of type errors everywhere, and you need to fix them all up. And after you've fixed all of your type errors, your refactoring is complete, you haven't forgotten any of them, and your program works. I've seen reported on the internet that when you do that, it usually works the first time, you haven't broken anything. But I don't think that's because of Haskell's strong typing system. I think that the fact that you know when to stop refactoring and you haven't forgotten anything is a benefit that you would get from any language with static typing, and Haskell has more than that, which allows refactoring to not break any code, and it's the fact that there is a set of guarantees in the language that if you rewrite the code in certain ways, the behavior of the code is guaranteed not to change. So in particular, you're guaranteed not to break anything, as long as you follow the rules. And that's not something we necessarily have, or at least we don't have as much focus on it in other languages. Another advantage of Haskell is that the code we write tends to be more reusable than in other languages. And the reason for that is that we tend to write code that it's much more abstract. We are not afraid of abstract nonsense words like categories and monads. In fact, we embrace them because that's the structures which occur when you generalize your code. It just so happens that those mathematical structures occur over and over again in very different kinds of code. And so, since it occurs everywhere, we can use the code which is specific to monads in all of those different circumstances. Haskell code is also easier to parallelize, which is very important in our modern world of multi-core machines. And the reason for that is that in Haskell, our code tends not to have any assignments, or very few of them. And for this reason, we don't have any race conditions. If I may remind you, a race condition happens when you have two threads and they both access the same memory location, and at least one of those two threads writes to that memory location. But if we don't have any assignments, then none of those threads is going to write to the memory location. And so we don't have to do anything to avoid race conditions, and so all of our code is already thread safe by default because it doesn't use any assignments. Whereas in other languages, like at work right now, we're struggling with a very large C++ code base, and we have to audit it and figure out what are the problematic areas where there are code which is not thread safe. And in Haskell, we don't have this problem. One last advantage on this slide is that Haskell code has fewer bugs. There are several reasons for that as well. The main one has to do with the fact that Haskell has a very precise type system, which allows you to encode some of your invariants, a trivial one being whether a pointer can or cannot be null. And so we're never surprised to receive a pointer which turns out to be null. The only way we can receive a pointer which turns out to be null is if we've specified that we expect that it could be null. And so we will probably check whether it's null or not. And there are much more precise invariants that we can encode into the type system. And the fact that the compiler knows about our invariants and can catch those errors at compile time means that there are fewer errors at runtime. So fewer bugs. Aliasing issues is another kind of bugs that don't tend to occur in Haskell, and that's related to the fact that we don't have assignments. It's very similar to the case with the two threads, except this time, instead of having two threads which write to the same location, we have two different areas of the code which refer to the same structure, and maybe they don't realize that somebody else has a pointer to that structure and modifies it. And the logic of the other part of the code is not ready to handle the modified structure. It expects it to see the same, and so it behaves differently, and it crashes or something, or maybe there's a correctness bug. All right, so that was a long list of advantages for Haskell, so what's the catch? Well, the big catch is that Haskell is much harder to learn than other languages. And the reason it's harder to learn is because of all of those things I've written on the left. The fact that there's a lot of implicit code is very good when you know what this implicit code is and what it does for you. But when you're learning the language, the fact that there is some implicit code is problematic, because not only do you have to figure out what the code that you see is doing, but you also have to figure out that there is some more code that you don't see, and you have to figure out what it does. Categories and monads, that's very scary words that probably prevent lots of people from even trying to learn Haskell. It's not that the concepts themselves are particularly complex. They consist of very few moving parts. What makes them hard is the fact that they are very abstract, and it's harder to reason about abstract things than about concrete things, and I'll give examples later in the talk. The fact that we have no assignments nor null pointers is also very problematic if you have some experience with other languages, because that means that none of your go-to idioms, which involve assignments and pointers, will be transferable to Haskell, so you'll have to learn a whole new way of doing things. And this links to the main subject of my talk. In Haskell, we have a different way to do things, a different way to architecture our programs. Since Haskell's feature set is very different from the feature set of a more mainstream programming language with probably classes and inheritance, we can't design our programs in the same way using class diagrams and such. And so instead, we have a different set of ways to design Haskell programs, and I want to talk about Combinator libraries, but I also want to take a moment to tell you briefly about this one, making illegal states unrepresentable. This is something that is achieved via Haskell's very precise type system. If you don't allow null pointers statically, then you won't have null pointer exceptions. And in languages other than Haskell, it's very frustrating, because when I write code, I realize, oh, here, I know that there is some invariant. I know that I could encode it if only my type system was precise enough, but I'm not using Haskell, and so I'm using a weaker type system in which I'm not able to express those properties. And so I know that I'm writing error-prone code, I know it's going to bite me in the ass, but there's nothing I can do about it, because that language cannot make illegal states unrepresentable. I need to rely on my code not causing the state to become illegal. But that's not what I want to talk about today. I want to talk about Combinator libraries. The way in which I'm going to explain Combinator libraries is via a series of examples. I'm going to start very simple with something everybody already knows, Boolean expressions. After that, an example from real life in which I rewrote some code using Combinator libraries, and it allowed many bugs to disappear. And finally, I'm going to briefly talk about parser combinators, which is a very common situation in which Combinator libraries are used. And I'm not going to spend much time explaining how they're implemented, but I still want to present them to you briefly to give you an idea of the more complicated things that can be done using Combinator libraries. And also, I'm going to talk about a completely unrelated subject, which is comonads. A comonad is not a combinator, but in the meetup description for this talk, for a few weeks, it was saying that I would give my introductory talk about comonads. And comonads is really not an introductory subject, and so I don't know. But this gives me a bit of a situation with the audience, the intended audience, because, well, I'm giving an introductory talk, and some of you might be here to listen to this introduction and want to hear about Combinator libraries, but maybe others came here specifically for the comonads. And so I'm going to try to cover both, but keep in mind that they are unrelated. All right. So, Combinator libraries. So I want to give an example. I want to implement the same thing twice. Once without using Combinator libraries, that is without using Boolean expressions. I'll still be using Booleans, of course, but without using Boolean expressions. And then the same thing with Boolean expressions, and we'll see the advantages of doing it this way. And so I came up with a situation, a hypothetical situation in which we might want to use Booleans. Can you recognize what I tried to draw with my ASCII art? The dude on the left is Mario. You know that because it has a cap with an M on it. And so this is supposed to be the last screen of a dungeon in Super Mario Bros. Where Mario is trying to defeat Bowser in one of several ways. Either he has the flower power and he can shoot 5 fireballs at Bowser and then Bowser dies, or he can avoid the hammers and jump on the platform and jump and touch the axe, cut the rope, and the bridge falls down and Bowser falls into the lava. It's a very violent game when you think about it. And the other possibilities is, since Bowser is jumping, Mario can avoid the fire projectiles that Bowser is breathing out. You can avoid them and run under Bowser while he's jumping, and again touch the axe and send Bowser to his death. At the same time, there are several ways in which Mario can be defeated, either by touching one of the hammers, by touching Bowser itself, or one of the fire projectiles. So we want to know whether Mario has won this level, at least, in this frame, and that's our specification, what I just told you, that Mario wins if he shoots 5 fireballs at Bowser, if he touches the axe, but loses in those other conditions. Alright? So how shall we implement this? Well, back then, they probably were using like assembly language or something really low level, and so they probably did not use Boolean expressions. I'm going to use variables instead of registers and then modifying them according to some conditions. And so we're going to have a sequence of if statements in which we check each of the conditions that were specified in the specification and mutate our variables accordingly. So if our variables, that is counting the number of fireballs that has his Bowser is greater than 5, then we say that Mario has won. And if Mario managed to avoid all of the obstacles and touch the axe, which we can determine by calling a subroutine, which verifies if there's an intersection between Mario's sprite and some other sprite, in this case the axe, then again we mutate the variable to mention that Mario has won. And in all of those other cases where Mario is touching dangerous things, we are setting the flag to false to indicate that Mario did not win. Alright, so that was one way to implement it, and it's still quite readable. But we can make it even better if we use our modern Boolean expressions. And you would probably have used Boolean expressions right from the beginning and not have attempted this long sequence of ifs. So With Boolean expressions, it's shorter. We check all of the conditions in one big expression. Mario wins if the number of fireballs is greater than 5, or Mario touches the axe, but not if Mario touches any of the other things. It's much shorter, but it's also a bit harder to read because, well, the complexity, basically, of having some things inside of an or, inside of a not, inside of an and. And so this format encourages us to give intermediate names to the intermediate expressions. And this actually makes the code more readable than the version we had on the left, because now those intermediate names are documenting what the code is doing. So on the left, we don't have the concept of Bowser dying, but on the right, we do. We see that Bowser dies if the number of fireballs is greater than 5, or if Mario touches the axe. Mario dies in all of those circumstances, and Mario wins if Bowser dies and Mario doesn't. So I think it's shorter and clearer, which are advantages of using Combinator libraries that I'm going to talk in a moment after I explain what is a Combinator library, finally. Well, a Combinator library is what happens whenever you have a few primitive systems that do something, and they do it well, whatever, in their own way. It's a complete system. But now, in order to build more complicated system, instead of building bigger primitives, you reuse your existing primitives, and you take two systems, and you combine them into one bigger, slightly more complicated system, which you can in turn combine with another system to build a bigger and bigger system until you have your whole thing. So that's the essence of what Combinator libraries are about, and let's see how we've used this in our implementation with Boolean expressions. So our primitives, in this case, would be the conditions that were inside of our if statements on the left, right? We can compare numbers, we can call subroutines, which return booleans. Those are the primitives, and they're the same on the left and on the right. What is different on the right is that we now have combinators with which we can combine those primitives into a bigger system. In this case, our system is just a boolean. And so we can combine two Boolean expressions with and or with or, and let's not forget also our unary operators. We can combine one Boolean expression and negate it and get a new, slightly bigger, slightly more complicated expression. All right. So with this system, we have the advantages I've just mentioned, that the code is shorter, that it's more self-documenting because we gave intermediate names, and it's a style of architecture where you're really encouraged to give intermediate names. But the reason why we get those benefits is because all of the cost is hidden inside of the combinators, right? And so it's not really tricky to decide which combinators we need to use in order to build our system. That's usually quite obvious. The tricky part here is all in deciding which combinators we shall provide in our library. So if somebody else wrote the library, that's great. If it's us, it's more tricky. We need to spend some time finding the right primitives. And let me demonstrate that it's hard to find the right primitives by showing you that, in fact, we're missing very important primitives here. On the code, well, on both sides, actually, there's the same weird assumption that there's only one hammer and one fire projectile. And well, one Bowser, but there is only one Bowser. Whereas in the ASCII art I showed at the beginning, it was clear that there were many hammers. And if you've played the game, then you also know that Bowser can throw more than one fire projectile at you. There can be more than one on the screen at the same time. And so on the left, it's very obvious how we would fix that. If we had a list of hammers and a list of projectiles, then we would loop over them and then reuse our condition inside. Whereas on the right, it's much less obvious what to do about our expression. It feels as if we really need a for loop in order to go around this loop. And I claim that this is not a limitation of the idea of using Combinator libraries. Rather, it's a limitation of the languages we're used to use. Their combinators for Boolean expressions are not expressive enough. Only a few languages, such as Haskell and Python, have combinators such as any and all, which allow us to take a list of values at a predicate and return a Boolean indicating whether at least one or all of the values satisfy the predicate, which is exactly what we need in this case. And so now that we add this extra combinator, which maybe the language provides it, or maybe we can implement it ourselves if our language supports higher order functions. Now that we have this extra primitive, it's very easy to modify the expression on the right so that it's just as short as before and it's just as clear as before, and it's implemented purely in terms of combinators, no loops needed. Or rather, the loop is hidden inside of the combinator, because as the slide said earlier, all of the work is hidden inside of the combinators. That's where the secret sauce is. All right, so that was my first example. For my next example, I'll tell you a story with more ASCII art. So it happened at work. We were working on this mobile app paid by the client, in which it was a TV thing, and so we had like lots of logos of the different shows, which we had to preload at the beginning. And while we were preloading the images, we were displaying some boring splash screen with the logo, and our client saw that as an opportunity, because why display this boring logo when you can display a very entertaining ad? And so that was part of our specification. We display the splash screen and then the ad, and then once everything is loaded, we display the images. Now it turned out that if the user is on a Wi-Fi network or something and he can download the images very fast, then maybe the user doesn't have the time to see the ad for long enough. And since somebody is paying for this ad, well, we had as a requirement that the ad had to be shown for at least 3 seconds. It was an extra requirement. We did not have that requirement for the splash screen. We had to display it for a short amount of time, and if the images were loaded earlier, then we could skip it, no problem. But then we'd have to show the ad for 3 seconds after that, while nothing was loaded in the background. Alright, so that's not such a complex specification. Let's see how we implement it. Well, let's see. We begin by displaying the splash screen, and then we start a background thread, and we load all of the images, and once we're done, well, we'll need to notify the main thread somehow, so we'll need a callback. And in this callback, what do we do? Well, in the very simple version at the very beginning, we would be displaying the list of images that we've preloaded, but now that we know that we have an ad, well, that's what we should do instead. We should display the ad. But that's only if we receive this callback notification while we're still showing the splash screen. Perhaps we are already displaying the ads for some other reason, in which case we should now move on to display the images. But wait, that's only because of the extra requirement if the ad has been shown for long enough. And that means I need some extra state. I need to remember the time when I started displaying the ad, okay. So that's it for the first callback. There's a second callback when there's a timeout. I need to register this somewhere. And so inside of this callback, well, there's really 2 timeouts. I'm using the same callback in both cases. And either I'm still showing the splash screen, in which case the timeout means that, well, now it's time to display the ad screen. I've shown the splash screen for way too long. Or if I receive the timeout and I'm not showing the splash screen, it means I'm showing the ad screen. And then, well, I should move on and display the images, but that's only valid if the images are already loaded. That was a bug we forgot the first time. Okay. Anything else? Well, what if the user clicks on the ad? Do we still want to wait for 3 seconds, or do we immediately move on? But what if the images are not loaded yet? And okay, I'll have to re-go through all of my callbacks and see what this new requirement changes. That was supposed to be illustrating that it was a bit trickier than we thought at first. Did you get that vibe? Yeah, good. So we received lots of bug reports about this section of the code. Even though the specification is not that hard, it was quite tricky to get it right. And so after receiving one too many bug report, I decided to rewrite it using Combinator libraries. And then there never was another bug report again, about this part of the code at least. So let's see, a Combinator library, what do I want? What is the system I'm representing? Well, I'm concerned about some event occurring after some other stuff happens. So we have a few primitive events, which are much simpler to handle when we don't have all of those events occurring at the same time. We're only concerned about one event at a time, and that's our primitive. So, well, we know that there's a timeout. That's one kind of system where you start the system, a few seconds elapse, and then the event occurs. There's also, we do some computation in the background. In this case, it's preloading the images, and once it's all done, the event occurs. And finally, if the user clicks on the ad, that's another of our primitives. And what would be our combinators? Well, the one I've found is if I have a list of such systems, well, their events occur at different intervals. And so I want the combined event to occur after they have all occurred. So in particular, it will occur at the same time as the last event. And similarly, I have another combinator, which is the opposite. I want it to occur when the first such event occurs. And it doesn't matter if any of the other events in the list occur after that. The combined event has already occurred at that point. All right, so it might not be obvious why I picked those particular combinators, but they work fine. Let's see how I can implement the same specification using a Combinator library instead of a whole bunch of callbacks and state. Because that's the whole point of using Combinator libraries. It's instead of building bigger system by adding more callbacks and more state, you only build bigger system from smaller system by combining them with other system and gradually building the complexity without explicitly adding more state. All right, so how do we implement this? Well, as before, we just put a splash screen and then we load the images. But this time, instead of installing a callback, we are describing a standalone system, which is the loading of the images, and all it does is it loads the images in the background, and once it's done, we have an event. And now, using this system, I'll be able to build bigger systems, such as the splash screen. The event, in this case, would be when the splash screen is done, when we are ready to move on to the next screen. And it occurs either when the images are fully loaded, in which case we want to display the ad while nothing is occurring in the background, or when the timeout occurs, in which case we want to move on and display the ads and still load stuff in the background, right? So we want to end the splash screen when the images are loaded or the timeout occurs, whichever comes first. And then we show the ads, and I haven't written it here, but I launch the next timeout, which I then use to define when the ad is done, which is exactly the same kind of events. It's again whether the images are loaded and its own timeout, but now I want to move on when one of those two events occur, whichever comes last. Because I only want to move on if both the images are loaded and the user has seen the ad for 3 seconds. And after that, of course, we display the images. So wasn't that much shorter and much easier to follow than my previous implementation based on callbacks? I'm still kind of using callbacks, using this on something pseudo-syntax, and that's because in my actual implementation, well, I had callbacks coming from the system. The Android system was telling me that there was a click or a timeout or something, and so I had to find a way to get my system to communicate with the system events, like the callbacks that come from somewhere else. And so this on something something part is not part of the system I'm building, it is something outside of it, which is using the system to determine how the non-combinator library part proceeds. And by the way, there are systems which are a bit more complicated than mine, where several events occur, and you can say what happens in all of those cases. And they're called functional reactive libraries. Look it up. All right, so we've seen another benefit. As I've said, I had lots of bug reports, I re-implemented it using Combinator libraries, and then I never had a bug report again. And so this tells us that using Combinator libraries allows us to make fewer mistakes. And, well, it's an anecdotal evidence that I'm giving you, but I think there's also a deeper reason why there are fewer mistakes that are being done when we're using Combinator libraries. And I think, in addition to the fact that it's shorter and clearer, it's also because each system is consistent. In my case, the systems I'm building, that's an invariant of my systems that there is one event that may occur, and if it occurs, that's it, it will not occur again. Whereas with the callback system, I did not have such a guarantee, and so it was harder to reason about what could happen when. Whereas now, I have systems that satisfy this property, and I make sure when I implement my combinators that the bigger systems also have this property. And so regardless of how many I combine, I always know that at least this is true. This helps me reason about the correctness of my program. Another benefit that I haven't shown yet, but I'm about to do it right now, is that it's easier to change. Earlier I was panicking a bit when I realized, oh, what if the user clicks on the ad? It changes all of the logic and I'll have to re-look at all of my calls back and figures out what changes because of it. Whereas now with this implementation, it's much more obvious what I should change. If the user clicks on the ad, well, it's certainly related to this line because it's the only line which talks about the ad, and it's certainly related to this part because, well, the image loading is not affected by clicking. The only thing that is affected is whether we're still waiting 3 seconds or not. So let's refactor this and give it a name. That the timeout occurs after 3 seconds. What this means is that the user has now seen the ad, right? Well, now, when the user is allowed to click on the ad, what it means is that the user is now expressing that the user has seen the ad. And so we're now allowed to move on without having to wait 3 seconds. All right. So there's another cost I would like to talk about, and it's the fact that the combinators, not only is it harder to figure out which combinators you need, but even if you're using an existing system and the combinators have already been picked for you, they're harder to understand because the combinators are more abstract. And in general, it's harder to reason about abstract stuff than about concrete stuff. Earlier, I was describing my combinators and I was saying that, oh, you have this list of events, or rather a list of systems, and each of them has an event, and the combined event occurs when the first of them occurs, and then later events, they don't affect it because the event has already occurred. And perhaps it's a bit strange, and you might wonder, well, why do you want that? Whereas if I tell you very concrete stuff, such as, well, you're waiting for the images to be loaded, and you're waiting for a timeout, and whichever comes first, now it means it's time to move on to the next activity. It's more concrete, it's much easier to think about. So that's a disadvantage. When you look at the definition of the combinators themselves, they're abstract, they're not concrete. And now I'm going to give an example, another example, that shows how important it is for things to be concrete in order to understand them. And I'm going to do this by explaining something that is very abstract, namely monads! It's a word that is scary and has probably prevented many people from trying to learn Haskell. It's not that scary. I'm going to explain it to you right now. It will only take a few lines. It basically means that you are sequencing two systems. In the case of events, what this means is that we start the first system, eventually its event occurs, And now this is our queue to start the second system, and eventually its event occurs. And the event of the combined system is now considered to have occurred at the same time as the event from the second system. But in order to really make this monadic, and not just sequential, we need to add a little twist, which is that since the second system is only being run after the first system has completed, well, we don't really need to specify upfront exactly what the second system is until that time. And so in particular, we can use a value that was computed by the first system in order to decide what the second system should be. And that's it. If you add this condition, then the combinator becomes monadic. And wasn't that abstract and hard to follow, right? Let me give you a concrete example of such a system, and it will be much clearer. If instead of fetching the images from the server in the background, I was actually fetching some configuration file telling me which users have paid to remove the ads, then once I have finally received this information, the next step would either be to display the ad or to display the app, depending on what information I have received in the first step. So that's an example of deciding what the second system should be depending on the result that was computed during the first system. Wasn't that much easier to follow with a concrete example, right? All right, so the reason why monadic composition as a name, monadic composition, that's its name, is because it's a kind of composition, a kind of combinator that occurs over and over again in many different combinator libraries. And so I'm going to give another example right now with my last example, parser combinators. Parsing is an area which is very well suited for combinator libraries because the languages we're parsing are typically defined using some context-free grammars or extended Backus-Nor format, and this specification is itself made out of primitives and combinators. There's one which is very visible here, which is stating that there's an alternative between two systems. Here we're saying that JSON expression is either this sequence of characters, or this sequence of characters, or this sequence of characters, or a string, or a number, or this particular combined system, which represents a list, right? And so our parsers can be defined using primitives and combinators which match all of the elements from the Backus-Nor format. So let's look at those primitives in more details. I'm very suspicious of this one here. It's clearly a sequence of two things, one after the other, but it's not quite monadic composition because there isn't the twist where the second part can depend on the value computed by the first. And so, well, it's suspicious to me because I've designed lots of combinator libraries, and I know that monadic composition occurs over and over all the time. And if I am following the guidelines that Haskell gives me by telling me that monads are important, and if I try to shoehorn my system so that monadic composition exists in my system, then so far I've usually gotten better systems that are more powerful or easier to use or something. So let's see what would happen if we were to extend this particular combinator so that it becomes a monadic composition. Well, what we need is to give a name to whatever is parsed by the first part, and now we'll be able to use this name in the second part. And that's it. That's what monadic composition is all about, the fact that the second part is determined from the first part. So what would this look like? In which circumstance could we use it? Well, if we were trying to parse XML instead of JSON, in the context-free grammar version, we would have to say that the first part where the tag is opened has an identifier, and in the closing tag it has some other identifier, and it will only be in a later pass that we would verify whether those identifiers are the same, and otherwise reject the file. But if we have this monadic form of sequence, then instead we can give a name to this identifier and say that the second part needs to be the same identifier. And now we no longer need to have a second phase where we validate that it's the same identifier, because our language already specifies that it is the same. It's no longer context-free, but who cares? We know how to parse this. And so that was extra power that was given to us just by trying to fit our system into the mold of monadic composition. All right, so monadic composition was great. What about comonads? Are they also great? Well, no, they're not great in the same way. But I'm still going to cover them. Keep in mind, I'm just talking about them because I'm supposed to talk about them according to the description. They have nothing to do with combinators. But they are related to monads, and so let's review monads and then see how comonads relate. So, one big part of creating combinators is that a combinator takes two systems and it builds a bigger system. But monadic composition is weird and different. It does take a system as its first argument, and it is producing a system. But what is this weird second argument? It's not a system. Because we're not specifying up front what the second system is. We're using a value computed by the first system to determine what the second system is. And so the type of the second part is actually a function from a value, the value computed by the first system, to a system, the second system. Okay, so, well, that's a function from a value to a system. And when we add the prefix co to something, it's usually because there are some arrows that are going to get reversed somewhere, in some category, whatever. So in this case, there's only one arrow that is visible, and that's the arrow which is being reversed. And so in the comonadic extension, we also have this structure where there's a system in the first argument and the combined thing is a system, but now the second part, instead of being a function from a value to a system, the arrow is flipped, and so it goes in the other direction. It's from a system to a value. Here, from a system to a value. So why do we want that? What would this be useful for? Well, it turns out that comonads are useful in a circumstance where you have a system which consists of many similar parts, and one of those parts is our focus. We're looking at it specifically, and the other ones are around it. And now we're trying to transform the system, and that's why here we have a function that takes the system and transforms it. And it only returns one value because we're focusing on one particular part of the system, right? And we're computing what is the new value for this part and not the others. And by applying this function to all of the parts of the system, we eventually get a new value for all of those parts, and so we have a new system where all of the parts have been updated. And as before, there's a twist. It's not just updating all of the parts independently from each other, because that would just be a functor. It would be fmap if you're familiar with that part of Haskell. And so the twist is that not only are we transforming the particular value under focus, we're transforming it by looking at the values of the neighbors around this focused value and also at the shape of the neighborhood around this value. And in fact, that's why we're receiving a system. It wouldn't really make much sense if we had a system and a function from that very same system to a value. It would make sense to have a fancy system like comonadic extension in order to do something with it, because we could just apply the function to the system. But that's not what's being done here. We're not receiving exactly this system. We're receiving slightly modified version of this system, where the thing that is modified is that the focus is different. The focus moved from each of the different parts of the system is looked at one at a time, and then we transform with it focused, and then the next one, and then the next one, and eventually all of the parts of the system are being transformed by this function. All right, so wasn't that another example of something really abstract and really hard to understand? So I'm going to give a concrete example, and now everything is going to be clear. Let's see. A very typical example of a comonad is a cellular automaton, because it's a system which consists of many parts, many cells, and each of those cells is either white or black. And there are rules in a cellular automaton which determines what's the new color of a cell, and this rule depends, well, in the case of Wolfram Rule 22, the rule is if you look at a particular cell and you look at its two neighbors, if there's exactly one of those three cells which is black, then the current cell we're looking at becomes black. So in this case, this cell would remain black, but also these two cells would become black because their three neighbors, including themselves, include exactly one black cell, and similarly for this side. So I'm not going to animate this cellular automaton, I'm going to put the next iteration below it. And then we can continue the logic. We can see, okay, so which cells are going to become black? Well, this cell has exactly one black neighbor, but this cell is going to turn back white because it has two black neighbors. This one has three, this one has two, this one has one again, and so it's going to be those two cells that become black. And if we continue the pattern a few times, we get a nice pattern. It looks like a Triforce in Zelda, and isn't that great? That's cellular automaton. But what's the link between this concrete stuff I've just explained and the really abstract comonadic stuff from the previous slide? Well, we have a system, namely one of those rows, and it consists of many parts of those cells, and each of them has a value, either white or black. It could be represented by a Boolean. And so that would be the first argument to comonadic extension. It would be one such row. And now the second argument would be the rule. That is a function from a focused system to a value. So if we focus on this cell, then we can return the value black, because we can look at its neighbors and determine that it should be black. And so this same rule is being applied to every single cell one at a time, and therefore the result of comonadic extension is this new system where all of the cells have been updated independently, but while looking at their neighbors. I also said that we were allowed to look at the shape of our neighborhood, and I'll now show you what I mean. Here, now that we've reached the side of our structure, we have a little bit of an ambiguity, because, well, what are the neighbors of these cells? Is it those two cells? And we again use the rule that it should become black if there's only one neighbor which is black, which is the case, and so it becomes or remains black. Or should we instead say that when you reach the side, then the structure somehow wraps around, and now this cell actually has three neighbors, like all of the other cells, namely those two and this one. And so two of them are black, and so the cell would become white. Well, that's a choice we take. And when we are implementing which choice we take, we need to do so by knowing whether the cell we're currently looking at is at the border or not. And that's what I mean when I'm saying that in our function, the second argument to comonadic extension, this function is allowed to look not only at the value of the neighbors, whether they're white or black, but also at the shape of the local neighborhood, whether you're at the edge or somewhere in the middle. All right, so if you'd like to join one of the many people who like to complain on the internet that my explanations of monads and comonads are simplified and incomplete, then come to our board game meeting next month. So every 2 months we have a presentation about some Haskell topic, and the other month we meet for beer and board game at our local board game pub. And so come and tell me that I'm wrong about comonads. If you have any other questions, now's the time. Type them in the comments below. Ciao!